Alright, welcome back to particle physics and the standard model. This is lecture 33, and last time we saw how to build the Yukawa sector of the standard model involving the Higgs, correct? This we did in order to understand how the fermions could get a mass in a chiral theory, right? Remember, in the standard model, because of gauge invariance, the fermions were forced to be massless, right, because you necessarily had to marry a left handed field with a right handed field, and since the left handed fields alone are charged under SU2, you could not have had a mass, and the bandage that we put in here was to introduce a new field, the Higgs field, which is a doublet under SU2, and once you have the quantum number specified this way, you cannot help writing down interactions of the Higgs field with left handed and right handed fermions, correct. And in that process we also saw how to give an interaction term for the QL and the UR fields using sort of a new field that we defined as a H tilde in terms of the second Pauli matrix and H star, right. And we saw that that is completely okay because this term is still invariant under SU2, right. We took infinitesimal transformations and convinced ourselves that that was true. So, once we had that, we could write down the kinetic term of the Higgs field itself, and we in that process we had to write down the covariant derivative involving the W bosons and the B boson, and we began to saw how one could give a mass to both the gauge bosons and the fermions, which was that if only there were some mechanism by which we could replace this entire doublet Higgs field with some constant, right. If something happened such that you just replace the field with a constant, if we call that constant V, then we find that the fermions and the gauge bosons would acquire masses that are of the order V, right. That is what we see from the interaction terms here and the interaction terms here, right, the interactions of the Higgs field with the gauge bosons and the fermions. Very good. So, today we will see how really this could happen, okay. How can we turn a field into a number, okay. That is the magic of symmetry breaking, okay. All right. First of all, let us try to understand this term. Why did we say symmetry breaking here? Because would you agree that if I were to replace this entire H field with some constant, then all these beautiful symmetries that we wrote down, the SU2 and the U1 and all that would just go away, agreed? Necessarily this field was invented in order to write down the symmetric terms, right, all the gauge symmetries, right. So, you can already begin to see that if I replace the scalar doublet field, see I keep emphasizing the doublet part, right, it is not just some scalar field, it is a doublet under SU2. So, if I were to replace it with a constant, then you would just like that simultaneously lose this symmetry, right, of the standard model, right. So, that shows that these two things happen together, okay. What are the two things? That when you lose the symmetry, that is tantamount, that is it is equivalent to a gain of mass, that is the you get masses for the gauge bosons and the fermions, okay. So, when you think of how masses are acquired, you should start thinking about symmetry breaking, that is more or less the only mechanism that we know of how elementary particles can acquire mass. Okay. So, how does this happen? Okay. What really could break a symmetry? The SU2 symmetry in the problem. Okay. So, I am going to first give you, I am going to detail a mechanism that to me is a simple way to introduce the entire concept of symmetry breaking, okay, so that you can see some of these things manifestly. And then I am going to tell you that this is not really the mechanism that nature has chosen. There is a somewhat more counterintuitive mechanism that really is going on in nature, and that is the Higgs mechanism. Okay. But first I am going to show you one way in which symmetry can be broken, but nature just did not take this route in our universe at least. Okay. So, symmetry breaking round 1. Okay. Okay. So, the symmetry physically, right, could be lost and is indeed lost when you in the basically it happens in the potential itself. Okay. So, what is the potential? See, in the Lagrangian I have a mass term, I have written the kinetic term, right, but then the Lagrangian also contains what? So, the Lagrangian, let me first make sure I get this right. So, the Lagrangian contains the kinetic terms, right, all the kinetic terms, right, for all the fields, and then it could have what? Interaction terms, right, interactions among the fields at least, right, and I could either lump the potential into this, or I could explicitly write there is also some potential. Agreed? Remember, the Lagrangian is kinetic energy minus potential energy in classical mechanics. That is the concept that we have here also. Okay. The idea is, in the Lagrangian you have to write down all the terms that are symmetric under Lorentz transformations and gauge transformations, right. In that you can always isolate a part that you cannot put into the kinetic terms, and you cannot put into interactions of fields with other fields and so on. Okay. So, in other words, to be even more specific, this is a potential that you can construct in terms of the scalar fields in the problem. Okay. So, with that in mind, what can be the potential I can write down? There is of course the mass term for the Higgs that I can write down, right. Remember, we used to write phi dagger phi, that is what I am writing here. H is nothing but the phi, but you have to think of it as a doublet now. Okay. So, I am going to call that mass mu squared, because that is the conventional name given to it. Okay. What else can I write? And I want to write only terms of dimension 4. Okay. Can I write a cubic term if I want to satisfy the symmetries? I can't, right. So, a cubic term would look like this. Now, this is SU2 invariant and this is not, correct. Similarly, I cannot write just a linear term, correct, but we are going to see in what sense we actually can write such terms. Okay. So, let me write the other term that is possible, which is a quartic term. Do you agree that this is invariant under SU2? So, this I can always write. Okay. So, in the normal course of things, I will just stop here, right. These are the only two terms I can write in the potential. Okay. And now, if something happened in nature, okay, such that the physically some phenomenon happened such that imagine it introduced, let me write that in red, imagine a physical mechanism, okay, introduced a linear term here, okay. So if it is linear, then for to satisfy dimensions I should put something out here, right. So some quantity with dimension 3, right. So let me just call it lambda cubed for now. Imagine, and of course there is a Hermitian conjugate because the potential is real, right. So if something were to introduce this term, would you agree that the entire symmetry is broken? It is no longer under invariant under SU2. Now this might sound a bit weird to you, but actually this kind of thing does happen in nature, okay. Initially you did not, so let me try to, okay, I cannot close this on my, I cannot close it with my hands, but imagine the red term was not there in the beginning, but it was introduced dynamically, okay, and I use that word actually in a technical sense. Something happened dynamically in the universe and then this term got introduced into the Lagrangian, then just like that something you broke the symmetry, and once you break the symmetry, let us see what happens, okay. Once you break the symmetry, at this point it should be somewhat intuitive that the gauge bosons and the fermions acquire a mass, right, okay. So how could this happen, okay. Now imagine you are in a universe, okay, where the QCD scale is very high, okay. So what is the QCD scale in our universe? It is around 100 MeV, right, order 100 MeV. So let me just write it that way, it is order 100 MeV, right, okay. Imagine that the electroweak scale was smaller than this, okay, or that the QCD scale is much larger than what it is in our universe, okay. What could happen is, see, remember these Yukawa terms, right. I am going to rewrite the Yukawa terms in this fashion, okay. I am going to say that the Lagrangian contains Yukawa terms that I am going to write like this, okay. So I am going to call this lambda tilde, and I am going to put an I, and I am going to write an H plus the Hermitian conjugate, okay, and the I runs over all the flavors of the quarks, right. So at energies below the QCD scale, okay, the universe started out with very large energies, right, but the universe kept cooling down as the energies got below the QCD scale, right, which is also the confinement scale, right. There is a phase that the quarks could form, in fact they do form it, okay. The quarks basically, okay, form a condensate, okay, called a quark condensate. So what does this mean physically? Remember in superfluidity, how does superfluidity happen? You have all these electrons going around, right, or take superconductivity, whatever, okay, take superfluidity, you have all these electrons floating around and then suddenly the viscosity goes to something close to 0, right, as you cool down the fluid. How does that happen, right? Or take superfluid helium, what happens there? You form Cooper pairs, correct, where two electrons pair up into something like a bound state, right. And in superconductivity also you have this, right. In fact, this is what I am talking about is indeed superconductivity, and in superfluidity you have two helium nuclei pairing up into a Cooper pair, correct. So, this forms a bosonic state, right, as opposed to a fermionic state, which are the individual electrons, right. So, remember this, and because you need to know describe the superfluid using these degrees of freedom, you no longer have resistance and viscosity and so on, correct. Similarly, as the universe cools down, the quarks form something like a Cooper pair, okay. This is not a meson, let me write that down. Although I have written a q bar q, this is not a meson. Mesons come as a different physical concept, okay. Literally these form something very much like a Cooper pair, and that is in fact what is basically a stepping stone to forming confinement, actually giving confinement, okay. So, this is basically something that you get as a phase of QCD, okay, a phase of matter where quarks form something like a Cooper pair, and that is called a quark condensate. And at this point, when this happens, you have to think of the q bar q, okay, as a single fermionic entity, sorry, bosonic entity, okay. And not only that, in the Lagrangian, this entire condensate takes a certain value, okay. It basically forms a constant value, it contributes a constant energy, okay. And that constant, because it, see now what is the dimensions of q bar q? It is 3, right. So, I need to write something with 3 powers of the energy, right. So, that is generally written as f pi cubed, okay, where f pi has a value of 93 MeV. So, better to think of this as the name that I like is, it is a chiral symmetry breaking scale, okay. Why is that? Again, we had a chiral theory here, right. We had a left handed field and a right handed field, and everything was massless. And remember, this is exactly what we called a chiral theory, because you can have a Lagrangian for the left handed fields independent of the Lagrangian for the right handed fields. Here you will put them together into an interaction, okay, that is a different thing, right. But the kinetic terms are basically independent of each other, they could be independent propagating degrees of freedom, right, and they could be charged differently under gauge groups. So, we actually had a chiral theory, but dynamically without doing anything, just like that, by cooling down and getting into confinement, right, which is something that nobody really understands except for the fact that you do have to form a quark condensate. Just by that, we have now put the left handed and right handed fields together into one condensate, into one entity, right. So, just like that, we have also broken chiral symmetry, right. That is what has happened here, okay. So, there is a chiral at low energy QCD, you had a chiral symmetry and you broke it dynamically, right. So, let me write that down. So, you broken chiral symmetry dynamically, that is, you didn't do anything, the universe just broke it for you, right, just by cooling down, and that gave rise to a term like this, and you broke, okay, electroweak symmetry, that is SU2 cross U1, you broke the electroweak symmetry explicitly, right. Why explicitly? Literally now there was another term introduced for you that just like that broke the electroweak symmetry at the potential level here, right. So, to me this is a simpler way to think of symmetry breaking. Something happened in the universe dynamically, and then just like that the symmetry structure here that we were working with got broken. Okay. Good. So, let us see whether this really could be the mechanism that nature chose for us. Okay. So, as you can see, I am going to replace the lambda with an f pi now, because we now know what that scale actually is, right. Okay. Not only that, I am going to give the correct coefficient. So, I am going to put let us call this just lambda tilde. Okay, you have to remember this is actually a sum over all the quark flavors. Okay, that is what this is, but for our discussion let us just call it by one coefficient, by one quartic term, which is lambda tilde. Sorry, not a quartic term, the coupling of the single Higgs term. So, this is sometimes called a tadpole term. So, I will just write that down. This is a tadpole term. Why tadpole? Because in a Feynman diagram, right, if I want to draw the vertex, it will look like this, right, whereas this vertex I can write as a mass, this vertex is a quartic, this vertex looks like a tadpole basically. Okay. Okay, excellent. Now let us see how this could lead to symmetry breaking, okay, or whether this symmetry breaking can actually describe our real world. Okay. So, it will help to draw the potential for us to visualize what is going on. Okay. So, I will just do that now, and notice that there are actually 4 degrees of freedom in the H dagger, right. It is a doublet and it is a complex doublet, right. So, I can write the H as a H1, H2 with H1 and H2 both complex fields. Okay. So, I am going to draw this in, because I do not know how to draw in 4 dimensions, I am just going to draw it in these 2 dimensions, where I am just going to pick the real part of H1. Okay. You can pick the imaginary part if you want, you can pick the other 2 possibilities also, real and imaginary parts of H2, and that is the potential. So, I am going to basically what I am seeing is a projection of the entire potential. Okay. Now, without the f pi cube term, right, how would it look generically? So, down here it will look quadratic, correct. This is what the mu square determines, and then as I go to larger values of h, the quartic term will start dominating, right. So, I can imagine that the potential looks like this. Okay. Let me just write, this is without the f pi cube term. Okay. Now, with the f by cube term, how would things look? I have added an extra term, an extra tadpole term. Would you agree that if lambda tilde is positive, the whole thing gets shifted a bit to the right? Not only that, I will not hit the minimum will be shifted to the right basically. Do you agree? So, what I have to do here is to make it pass through 0, because when h is equal to 0, the potential goes to 0, right. So, I will do that, but then as you can see, the minimum has shifted to the right. Okay. Clearly already you can see that this is not symmetric, right. This one was symmetric. If you take h2 minus h for instance, that symmetry is preserved. And you can also imagine that if I rotate among h1, h2, I mean real part of h1, imaginary part of h1, real part of h2 and imaginary part of h2, this potential is still symmetric under that rotation, right. Whereas this potential, the green potential, has explicitly broken that symmetry. It looks explicitly asymmetric, right. So, this is definitely one way in which symmetry breaking could happen. Now, let us try to find the value of this minimum. Okay. So, where does the minimum come? Instead of actually doing the calculus and solving for the minimum, I am going to consider a couple of these cases. Okay. And to make life easier, I am going to think of these in terms of real fields, okay, but they can be generalized easily to all the 4 dimensions in field space. Okay. I am just going to take a simple, I am going to simplify the potential to just mu squared phi squared, okay, plus lambda phi to the 4th plus lambda tilde phi plus the Hermitian conjugate. Okay. So, let us parametrically look at what the minima could be. Okay. Now, and the other thing I am going to do is I am going to call the minimum in this language. Okay. This literally means, you know, this is the expectation value at the vacuum. Okay. Remember the vacuum in Fock space, right. So, this is the vacuum expectation value, that is literally the technical term for it. Sometimes people just say VEV as the short form. Okay. So, even here when I wrote the q bar q, the meaning of it is that it is the vacuum expectation value of the q bar q. Okay. That is what it means. Okay, excellent. So, now let us look at one particular limit, okay, and then I will wrap up this lecture. In the next lecture we will see the other limit and then go on to the realistic way of doing symmetry breaking, okay, the real way of doing it, the real world way of doing it. Good. Now, imagine, okay, that at the minimum, all right, imagine that the first term was smaller. So, what happens at the minimum? Let us first write down the condition for the minimum. Okay. So, this is the condition, right. That would give me so now I am not going to write the expectation the Hermitian conjugate. Okay. So, that is the condition, right. Now, imagine that at the minimum, okay, this term by the way I should have written f pi cubed, right, that is the most important. So, f pi cubed f pi cubed. Okay. Suppose so generically I expect the lambdas to be order 1, right. So imagine I am in this limit where mu square phi at the minimum is much smaller than f pi cubed. Okay. So what happens? I can now neglect the first term, right. And that means I am left with only this as the condition, correct, to be put into the minimum condition, and I would get the vacuum expectation value. That is the reason why we call it V, as you can see it now, right, which is the Higgs, okay, in this case just phi, but it is also the Higgs, okay. This is also the, because we are actually talking about the Higgs, we are just generalizing or rather simplifying to a real phi. What would that be? From this condition I would get lambda tilde over lambda power 1/3, right. I am neglecting factors of 4 and things like that, okay. But the important thing is it is of the order f pi. So is this our world? Of course not, right. Why? F pi is around 100 MeV, right. Whereas we just saw that the gauge bosons, right, the gauge bosons are of order, the masses are of order V, we just saw that in the at the end of the previous lecture, right, when we replace H with V, and the fermion masses are some Yukawa couplings times V. Nevertheless, we have fermions that are like more than 100 GeV, the top quark is more than top quark is 173 GeV, right. So clearly this cannot be our world, clearly this possibility is ruled out. Things are not at 100 MeV, they are much higher. The W boson mass is what? It is around 80 GeV, right. So clearly this cannot be true, okay. So I will stop here. In the next lecture we will see another possibility in this dynamical symmetry breaking, and then we will move on to the actual spontaneous symmetry breaking that constitutes our Higgs mechanism, okay. All right, thank you, see you in the next class.